So some quick updates in terms of logistics. I guess we're kind of one lecture ahead on the syllabus. I think it said fossil, coal, and oil for lectures 5 through 7. So um, we've already covered the fossil fuels. So actually, we're going to have a double lectures on renewables. So that'll keep us on track. Um, the group assignments have been set. I did all of that last night. Everyone got one of their first three choices, unless you didn't fill out the form, uh, in which case you got randomly assigned into a group. And so I'm gonna send out those an initial email to each of the groups sometime today, and then it will be your responsibility uh, to send an email to schedule a meeting with your energy mentor um, sometime this week. If they can't meet this week, it's okay to meet next week. But do keep in mind the deadlines for these things, which were posted on the syllabus and the announcements on Canvas. Homework 1 is going to be due on Wednesday, so please make sure to submit that. And homework 2 will be starting on the same day. I'm also going to be posting a midterm practice test today or tomorrow. And then Monday, the actual lecture will be a little bit shorter, and we'll have we'll go over the practice tests and take questions and do a little bit of review before the midterm. Alrighty. So that covers just some of the basic logistics. So, okay, quick question before we move on. Will the midterm cover material from Monday's lecture? I think, I guess you're referring to next Monday. I don't know because I haven't written the midterm yet, but probably not, because I'd want the midterm to cover. I think what we'll do is we'll cover the midterm through next lecture on Wednesday. So everything up to the end of renewables. Okay, another question. Where are the project assignments posted? I haven't posted them yet. So right after lecture, I'll put them up. I'm trying to decide whether I'll send the groups individually or just post them all on Canvas. It'll be easier for me to just post it on Canvas, but I actually don't know if you guys have access to like other people's emails. I need to figure that out. Basics of renewable energy. Okay. So the last couple lectures, we've talked about a lot of the more traditional sources of energy, larger sources of energy, especially in regards to fossil fuels, right? So thinking about coal, crude oil, and natural gas. And as you guys are pretty familiar with by now, we know that the implications of the use of the energy, even though it's cheap and convenient, easy to use, there are a lot of negative externalities associated with them, especially in terms of emissions. And so we have started to transition away and think about renewable energy sources, both to address the resource availability and limitation issues, issues of like energy security, and lastly with emissions, and thinking about how to leverage these new types of sources of energy and electricity to basically accomplish all of those goals, and mitigate a lot of the drawbacks that we have with fossil fuel energy. So renewable energy is, right, by definition renewable. It's derived directly or indirectly from either the energy of the sun or the energy of the earth, which, yeah, right, in theory is not really perpetual and infinite, right? But for our purposes, it's basically an infinite energy source that we want to try and leverage. Okay, so what are all the different types of renewable energy? So you might be pretty familiar with solar and wind, right? So solar is from direct sunlight, wind is from wind that's created by difference in temperature gradients in the atmosphere. But there are a couple other ones that people less commonly associate with renewables, or maybe doesn't come immediately to mind when we think about renewables. So one of those is biomass. This is energy produced from photosynthesis. There's hydropower. So this is looking at difference in gradients. So we take advantage of the potential energy of water sort of moving down in elevation to get hydropower. There's also ocean, so that's tidal power, wave and waves. So getting motion from tides and waves, and actually even temperature differences in the ocean, and taking advantage of that. Ocean, by the way, I'll just quickly mention, we're probably not going to talk so much about that. Mainly what we'll focus on is solar, wind, and a little bit of biomass, a little bit of hydropower. Ocean power is right now pretty uneconomical, and the potential is fairly low. But we will maybe cover a little bit on Wednesday. And then geothermal is energy derived from heat in geological formations, and we'll show how that works. But geothermal is actually a pretty economical resource, but it can be hard to find the proper resources to take advantage of it. And so definitely exists. There's quite a few geothermal power plants around the country and around the world, but relatively it's still quite small. When we talk about the different types of renewable energy, I think everything but biomass is mainly for electricity, and then biomass can be both in electricity but also in transportation. So you may have heard of things like biodiesel and other forms of like bioethanol that you would use for blending with gasoline. So those are all types of transportation fuels. So taking out sort of biomass for the other five, in order of sort of most electricity produced worldwide, and we'll see more of this in a bit. But just to get your mindset in the right direction, hydropower is the largest, followed by wind, and then you've got solar and then geothermal. Ocean really isn't a thing at the large scale these days. Okay, so going over again why we think this is important. It's a key component of having both a sustainable and secure energy future. And so sustainability, really is referring to the fact that unlike all of the fossil fuel resources where we've shown, people estimate they're going to run out within order of magnitude hundreds of years, right? And so that's going to go away. But with renewables, you kind of have them perpetually. In terms of energy security strategies, so this is like the U.S. relying on Canada and Saudi Arabia for some of the oil imports, and so relying on other countries can be riskier for the economy, and so even if you don't consider climate change to be a problem, which it is, independent of that, there are also these other big benefits with regard to reducing dependence on things like foreign oil. But of course, they also provide this large GHG reduction, and it's one of the main strategies, right, to meet our climate change goals. There's sort of this dichotomy between people who point out that like, oh, renewable energy is a really small fraction or a relatively small fraction compared to fossil fuel energy for what we use today, which is true. But on the other hand, it's also expanding at a really, really rapid rate. So in 2019, 72% of all new sort of energy capacity installed is coming from renewable energy sources. Why are they good? Non-depletable. It's really widely available in many parts of the world. So when we think about the geographic distribution of like where fossil fuel resources are located, we can point to specific countries, right? So like the United States, Russia, Saudi Arabia, and those are the countries that take advantage of those resources to the greatest extent. But when it comes to renewables, right, it's not totally uniform across the world, but it's much more equally distributed, right? Every place in the world gets sunlight to some degree, and the wind resources probably a little bit more variable, but still widely available. They are currently more expensive, but are becoming increasingly economically competitive. And we'll talk in a lot more detail, maybe today, maybe on Wednesday, about some of the economics surrounding a lot of the renewables, how the prices have changed over time, what that means for their ability to compete with fossil fuel energy. Renewables are substitutable for, fossil fuels are substitutable by renewable energy sources. So all the sort of services that are provided by fossil fuels can, in theory, be served by renewable sources. And obviously, the big one that we really care about, or I think we really care about, are really deep cuts in our greenhouse gas emissions, right? That's one of the primary benefits of switching to renewables. But it's not all sort of benefits, right? There are some issues. They're generally higher cost. And less mature than fossil technologies, which means that having a new technology come in to compete against like an incumbent fossil fuel generator can be difficult. The environmental impacts are not totally zero, and so that's one thing to keep in mind, especially when we think about the life cycle framework. Yeah, when a solar panel is producing electricity, there are no like emissions associated with it, but you also have to think about the production of the solar panel, the installation of it, and then land use, water use impacts. Again, things we'll cover on Wednesday. The integration of renewables into existing energy systems can be pretty challenging. In a future lecture, when we talk about how the electricity grid works, it's particularly problematic because the sun doesn't always shine, which may be one of the more obvious ones, but there are a lot of other implications for solar, right? So if you, in California, we have this pretty interesting problem where there's so much solar being installed, both distributed solar, which is like things, solar on people's rooftops, as well as utility scale solar. So those are like the big fields of solar panels. There's so much of that happening that it's causing some pretty interesting issues in our electricity system, because there's a whole bunch of solar power being produced, and then all of a sudden, as the sun starts going down, you lose all of that, and that means that a bunch of other power plants need to turn on really quickly, and that can lead to different sorts of problems. Again, that's something we'll talk about once we get to our lecture about the electricity system. With especially with biofuels, and we've talked about this a little bit, there's potential interaction with other markets. So you might be competing against food, which is something that you really wouldn't want to do. Yeah, and then a whole sort of variety of social, institutional issues, and policy issues, which we'll delve into sort of throughout the lecture. Okay, how are renewables used? So this is actually a little bit older slide, and I'll show an update in just a second. You can see here of all the energy production, it's about 19% in 2015. Of that, it includes traditional biomass over here, and that can include things like burning for cooking, right? But a lot of what we're really sort of thinking about is with modern renewables, and so this is with heating and electricity, and so there's some geothermal, solar heat, and biomass, and a lot of this other stuff is for electricity. So when it comes to production of electricity in terms of the total energy use, you're talking about a little bit over 5%. And then this little rectangle here is for transport. So the more recent one in 2017 looks something like this. The number is going up a little, sorry. The number is going up a little bit over here. We're at like 5.6%. And you can see that there is growth happening. It's still a fairly small fraction, but again, the installation of new capacity is really sort of dominated by renewables. So you know, we're moving in the right direction. There's a question of if we're doing it fast enough, but for the most part, at least, the new stuff that's going in is renewable. So thinking specifically about electricity, so again, this one is actually one of the older slides that I'm drawing on. So this is about a quarter of global electricity is coming from renewables. And as I had mentioned before, the vast majority is hydropower. So hydro is larger than all the other sources of renewables when it comes to electricity combined. Wind power is in second. You've got biomass at 2%, and then solar at about 1.5%. Ocean power, CSP, which we'll talk about, concentrated solar power, and geothermal power at 0.4%. I would wager to guess that almost all of that is CSP and geothermal. There's probably like almost nothing from ocean And then more recent update, so 26%. So in the span of um, in the span of 2 years. So let's see, we went from 24.5% to 26%. Um, so that's a 2% increase per year, or 2% in 2 years. So maybe 1% per year. So probably still, even if we were to extrapolate that linearly, it would take us what, 75 years to go to total full renewable electricity, which would definitely be way slower than all of the climate targets that we're trying to meet. So there's that to keep in mind, but also keep in mind that it's not like a linear thing. As you have more and more renewables producing electricity, a lot of the problems that I briefly talked about about switching to renewables get really compounded. Um, and so intermittency issues, ramping issues, all of those get way crazier as you get to higher penetrations of renewable electricity. So it actually will get harder with the more renewables that we have. So that'll be important to keep in mind as well. um, if I jump back here really quickly, we can see one of the biggest growers. So solar PV went from 1.5% to 2.4%. So that's not quite double, but almost double in the span of 2 years. So solar has really grown, and I haven't seen the more sort of recent statistics in 2019 and sort of the beginning of 2020, but it would be interesting to see how much that's grown since then. This gives hopefully some sense of what the growth looks like. And you can see that probably the two biggest growers are going to be your PV, solar PV, solar photovoltaic, as well as wind. And so this is referring not to the amount of power that's produced, but the amount of capacity that's installed. Um, and so when we think about the total amounts worldwide, you're talking about cumulatively something on the order of 2 terawatts of capacity back in 2016. And then sort of at a high level, who is investing in renewable energy? So here, I think this gives a nice sort of sense of the amount of money that we're putting in to these things. So everything here, it's sort of on the order of billions of dollars. We can see the relative magnitudes of differences. Also, this isn't like scaled to population or anything, so you do need to keep that in mind. But you can see what the sort of relative trends are. Kind of flat for the US. There have been certain policies that have led to sudden investments, but we're talking on the order of probably around $40 billion per year. Whereas something like in Europe, there's actually quite a bit more, especially about a decade ago. They were investing maybe twice as much in renewables. I think it also has to do with some of the policies that were put in place. Germany, in particular, had a really aggressive solar policy, and so that led to pretty large energy investments there. You can see 2 up-and-coming players in Asia, and so this is excluding China and India, but for the rest of Asia, it's the investments in renewables has been growing sort of year over year, and you can see the same in China. And so they're definitely putting pretty serious amounts of money into investing in renewable energy, and that's reflected in the amount of energy and the capacity that's being installed in those countries. Um, who has the most in terms of capacity installed? Here we can have sort of a rank order list uh, of each of the renewable sources across all the countries and where they stand. Um, you can see for the US, there is quite a bit of investment and capacity across a whole slew of different renewables. Um, Whereas, specific countries are maybe targeting different sorts of renewables. So like Canada and Russia, for example, are 4 and 5 in hydropower, but don't hit any of the top 5 in other sources of renewables. Okay, continuing on. In terms of electricity generated, so this is more sort of normalized, I would say, because it's the share. And so even sort of regardless of size, we can see sort of percentage-wise how much renewables are being used to generate electricity. You'll note that in this case, it includes hydro, not just solar and wind, and that accounts for, again, the vast majority of renewables these days. So when you include hydro in renewable generation, your average is around a quarter of the total electricity production. So this is back in 2014. So if you remember back a couple slides, that number has already jumped up to 26%. Maybe last year and this year it'll be even higher, 26, 27%. Norway is the sort of biggest in terms of share of electricity. Almost all of their electricity is produced from hydropower, and so for countries like that, all the ones sort of in the top 5 or 6, right? You can see that anyone who's producing more than, say, about 50% of electricity, usually the majority of that is from hydro. I guess there is some exception in Denmark where they have a whole bunch of offshore wind and wind onshore, which produces most of their power. For the rest of us, we're all basically under 25%. So thinking specifically about the United States, the energy production and consumption, we're hopefully all fairly familiar with this portion of the pie chart: crude oil, natural gas, and coal. We produce 12% renewables, and consumption is about 10.4% renewables. So this is production. Most of that is going to be biomass, and so this doesn't just include electricity. This is all sources of energy. So that includes things going into transportation, for example, which is why when I say hydropower is the most, it's the most for electricity, and and there is more sort of primary energy or secondary energy in biomass that's being used for other purposes. Um, the electricity nameplate capacity by source. So there was a similar chart from before, but this one is specifically in the United States. Note that the units of power are pretty different. So cumulatively, we've got about 220 gigawatts of renewable capacity. Although that number may be slightly deceptive when you're thinking about power production, and we'll talk about why that is later on. But to give a general sense, probably the peak power demand in California is around 50 gigawatts. So what we have installed today in the US could serve basically, 4 Californias at absolute peak, right? So this is like 4 Californias in the middle of the summer with everyone running their AC. Yeah, if everything were producing at full power, that's the amount of renewable power that could be produced. But again, keep in mind that wind has a capacity factor around maybe 40%, and solar photovoltaic will have a capacity factor around 15 to 20%. So the total amount of electricity that's actually being produced from these guys is going to decrease by that percentage, or 1 minus that percentage. Yeah, so I see a question, where do those non-consumed energy go? So I think you're talking about the difference between production and consumption. Yeah, exactly. So a lot of that is going to be energy loss. So some of it, I would say the majority of it is going to be in biomass, because what you're producing from wind and solar for like electricity, that you're sending that through transmission lines, the losses from that are pretty small. They're like 1%, 1 to 2%. Whereas burning with biomass is going to be quite a bit lower, because you lose a bunch to heat. Hydropower, I bet that there is a fair bit of losses from pumped hydro, because otherwise the losses are coming in electricity, again, which is fairly small. And so we'll talk about what pumped hydro is in a little bit. So there's a question, non-consumed energy can't be reversed. Yeah, exactly. So anything that you're doing from losses to like heat or inefficiencies, that's just, yeah, lost energy. So if you remember our lecture about exergy, there's like useful energy. And so we're not, physically losing the energy, but the useful energy that we use gets lost essentially. Okay, as I mentioned, renewables are definitely the lion's share of new installations. So in terms of what are we building and then what is getting retired, we can see, so this is last year electricity capacity additions and retirements. So these are breakdown of things that were installed by month. And you can see in total, there were 24 gigawatts of capacity installed, where over half of that is solar and wind, and then about a third of that is natural gas. And you can see actually when it was installed over here. Yeah, actually, it's kind of interesting, not super uniform. I'm not exactly sure why a bunch of stuff got installed in December. I don't know if that's like a regular thing or It just happened to be like that this year. But in terms of like the additions, you can go back and look at similar charts. These are produced by the Energy Information Agency, and they're fairly similar over the last decade or so. Renewables and natural gas to some extent have been dominant in terms of new power installed. Planned retirements. So these are things that get mothballed or taken offline, essentially. So that includes some nuclear plants, some natural gas plants, but mainly coal plants. Coal plants are kind of like getting retired for several reasons. One of them is that they're just old and it's not worth retrofitting, especially when they're now competing against natural gas, which is a lot more economic. But they also are they're also getting retired because of stricter requirements for more renewables and for like emissions and pollutant standards that are more and more difficult to meet, or used to be more and more difficult to meet. We'll talk a little bit about some policies that have since been overturned since Trump came into office, and how that's affected some of the decision-making process in terms of installing things like coal and coal retirements. Okay. So now we'll sort of move on to talk about, so we've talked about, how they're being used now, and then the second sort of half of lecture, we're going to go through some of the theoretical potential of the actual like primary energy resource, thinking about how much is available, but in a different way than we talked about with fossil fuels, which is like in terms of reserves, how much you use before you run out. Whereas here, we're going to be talking about how much is readily available essentially every year, right? Because it's a renewable source, so you don't have that problem of running out. And then we'll talk about the technical potential, which has to do with the technology and what it's able to capture. And then we'll talk about the economic potential, so tying into the economic impact of having the renewables, as well as the economics and pricing surrounding the specific technologies. Okay, so you've seen this chart a couple times now. This refers to the amount of resources that are available. So with the limited ones, so oil, gas, coal, uranium, these are basically set stocks, whereas solar energy, hydro, wind are resources that are annually available. The total consumption by humans is this much. And so that'll give you some, again, perspective of what we're working with in terms of the energy available on this planet. And so when you've seen this chart before, maybe you've thought to yourself, well, the physical renewable resources is like way bigger than our current and probably foreseeable needs for primary energy, right? So like imagine how big this blue box would need to get for us to be like using all of this potential energy. So does that mean, okay, problem solved? Well, no. So there are lots of issues about how to get at that resource, right? And even if we could, they don't always match our energy demands because of intermittency issues, low energy density, which means it would be really hard to take advantage of, or inconvenient locations, right? So if you think about, all the land covered by cities versus the rest of land that's sort of available, not everything sort of this like flat, easy to install, close to cities, and has a lot of the like sun or wind or geothermal resources just like ready to go. And so that can really restrict our ability to get at the resource. The existing energy system is not well set up to incorporate renewables. And so these are some of those like electricity grid issues that I was mentioning. And then addressing a lot of these challenges has lots of high upfront costs. There's land issues, and there are still some environmental impacts. So as I was mentioning, there are different ways we can estimate resources. You've got your theoretical, your technical, and then your economic potential. And so that's essentially what we're going to be going over both today and on Wednesday. Theoretical potential is the maximum energy flow rate. So this is like, if I count up all the sunlight, like how much energy is that? Or if I measure all of the wind power blowing around on this planet, like how much is the sort of maximum energy? And then there is technical potential, which is, okay, if I have like a solar panel or a wind turbine, how much of the theoretical potential can I capture, right? Because this will take into account things like the efficiency of the system. And yes, technical potential can sort of change over time, right? As your solar panels get better and better, as your wind turbines get better and better, this definitely affects the technical potential. But all of this is sort of more engineering based and related to the technology that you're using. And then lastly, there is the economic potential. And so this is thinking about how much of the renewables that you could recover relative to that particular technology costing a specific amount of money, and comparing that to like burning something in fossil fuels. So there are like economic constraints and social constraints, thinking about will people, in addition to things about cost, but also things like, are people going to protest that I put a wind turbine in their backyard? Maybe they won't like that very much. So there are also social barriers that are included in what we consider to be economic potential. Yeah, so besides that, you've got geographic, environmental, and social factors that limit deployments. And some of the social factors I would actually kind of throw into economic potential, although you could in theory also keep them separate. Okay, so we're going to start off first with going through theoretical potential for things like solar, for wind, for hydropower, and for biomass.
There's a question.
Yes, okay. There's a question here. Thank you for that. So technical potential is based on the theoretical potential. It is, it's both thinking about theoretical potential and the technology. So the theoretical potential is like the most that you could get, and then the technical potential is like the most you can get with the technology that you have. So it's kind of it's based on both. Alrighty. Solar irradiance. So we have this, I think we've shown something like this before, but this gives an idea of how sort of solar radiation enters our atmosphere, and what's available to be captured. So solar radiation hits the atmosphere at about 1,300 watts per meter squared. You've got some that gets, where's my mouse? Here we go. some that gets absorbed in the atmosphere, in water vapor by clouds, and then hits the ground. Um, and some of it is absorbed, some of it is reflected. And so this is sort of the direct radiation. You also have irradiance coming from, the heat energy after sunlight is absorbed um, into your ground and into the atmosphere. And that radiation goes back into the atmosphere. And so you have a balance and equilibrium of energy coming in and energy going out. um, the so this should give you a sense that all the stuff, all the sunlight coming into the Earth isn't all sort of totally available to be captured by solar generation, right? So we're really concerned with all the stuff that comes down and is able to be absorbed on the surface. Also, as the angle of the sun changes throughout the year, you'll get sort of this fluctuation in the radiation on the surface and in the atmosphere, and that will have some effect on again the amount of solar energy that you can capture in say the summer versus in the winter. Yeah, so solar energy at the Earth's surface varies, as I was saying. So it's not only by the time of year, but also obviously by the time of day, but there are also solar cycles. And then the big one, probably the biggest one besides time of day, are atmospheric conditions. So you can have clouds and particles that will affect how much solar energy is available on the surface, as well as the altitude, right? So at higher altitudes, you may actually have more solar energy available because there's sort of less stuff that it's going through before it hits the surface. Theoretical solar potential is absolutely massive, right? And so again, going back to thinking about that big rectangular block, solar potential is easily the largest of all energy that's as a raw resource that's available. So we're talking sort of roughly order of magnitude 1,000 watts per meter squared. And after you account for weather, the fact that you have daytime, nighttime, seasonal variations, the annual average surface radiation is about 170 watts per meter squared. So this 1,000 is like really the maximum that you could get in exactly the right conditions at the right place on Earth's surface. But really, on average, you're getting closer to about 170 watts per meter squared. So if I go back to this example, right, our incoming is about 1,300, 1,400. And if you're high up in elevation and there's like nothing happening up here, then you're closer to, then you can get a max of about 1,000 watts per meter squared. But in reality, you get about 46 on average, 46%, and that's during the daytime. And so we get half that, sort of more on average with that whole diurnal variation. Then you're talking about closer to 170 watts per meter squared. So that's just to give kind of a rough estimate. There's going to be some discrepancies, like depending on the source that you're looking at. But anything around 200 is fairly reasonable. The total flux, in other words, the total amount of sunlight across the full Earth is about 3.9 million exajoules per year. Most of the surface of the Earth is oceans. So when we're talking about just on land, it's about 0.8 million exajoules per year. That's a lot of power. It's an incredible amount of energy. And just to give some sense, in 1 hour, uh, the amount of solar energy that hits the surface is about equal to all of human consumption through energy activities over one full year. Okay, I see a question. Oh, okay. I guess I answered it already. So scratch that. No question. Um, Back of the envelope. So this is kind of like a reference material for you. Gives some sense of uh, the numbers that you can keep in your mind roughly, or come back as a rough sort of estimate for things that you would need to look up if any of this is ever relevant in the future. So maximum insolation, in other words, the radiation hitting the surface, it's 1 kilowatt. If we were to convert that at about 10% efficiency, you're getting 100 watts per meter squared. But more sort of more relevant number would be about 200 watts per meter squared for your average annual installation. Okay, again, this is repeating from the previous slide. If we were to convert that to electricity at 10%, so that the average annual installation, not the maximum installation, so over the course of 1 year, like a 1 meter squared, you would be able to get about 175 kilowatt hours of electricity. Okay, so that's the amount of energy that like 1 meter squared of solar power would be able to generate over the course of an entire year. Yeah. So then, in terms of technology application, the area to charge or to power a conventional house would be maybe about 100 meters squared, so like a 10 by 10 meter square. That's like a typical rooftop. To charge an electric vehicle, you might need something like 20 meters squared, and to fuel your hydrogen fuel cell car, you might need something like 35 meters squared. That's just like a rough estimate to give a rough amount of energy for the demand that would be associated with a conventional house on like a daily, monthly, annual basis. This is a map of worldwide irradiation. So you can see basically the sort of pinker red is where you get the most, and sort of blue green is where you get the least. Obviously, sort of the nearer you are to the equator, you generally have more power available. If we look more specifically at the United States, you can see that there's a pretty good reason why we have a lot more solar on sort of the West Coast than on the East Coast, and in the South rather than in the North. It's just a lot more efficient. So when I think about going to the economics, if I am able to get something like 7.5 to up from 4, you're essentially able to produce twice as much electricity, so the economics of it are twice as good. So you're making twice as much money for the same amount of cost. So that can be, you know, a really big sort of driving factor if you're talking about right on the margin. If I'm like barely able to compete with a different resource, you know, doubling the cost is going to make it a lot less attractive. And so that's one of the issues with solar, is that like yeah, it may make sense to install it in certain locations, but it may not be sort of uniform across the whole country. Um, Not only that, the angle of the sun can play a pretty big role in uh, how available the resource is, and how much you can get from it. So something like a fixed panel, solar panel, versus a design where it moves and is able to take better advantage of the angle of the sunlight, can also see pretty different results in efficacy. So this is just gives you a sense of like, so in the winter, if this is your uh, sort of north to south, um, the sun will sort of go on this angle, on a shallower angle, whereas in the summer the sun would go in a steeper angle. And so if I were to like take that into account, you can see, roughly how that would change the potential of sunlight that I would be able to capture, right? And so if I were just to have it flat on the surface, um, the sunlight might look something like this, where you would lose a lot to the incidence of the sunlight, and so the amount that you would be able to get. So again, this is kind of like a qualitative example of the resource that you can capture. Um, it looks something like this. Whereas if you had an angled collector, you're getting sort of much better, right? And so even in areas that were like blue before, you're getting, this green, which would be make it equivalent to kind of the Southwest just by angling the solar. Yeah, so there's a question. So could you please explain the incidence, what the incidence of the sun is? Yeah, so that has to do with in different seasons, the the way the sunlight hits the earth, because of the position of where you are on Earth, the angle of sunlight will be different in the winter versus summer. That's why we have different seasons. That's why it gets warmer in the summer versus cooler in the winter. So incidence just refers to the angle. Um, and so when you have you can artificially sort of affect the incidence by angling your solar panel, right? And so when you align it in this way, it's able to collect more sunlight because it reflects less of it, if you're facing directly. And then if you have a tracking plate, and so this example is if it's flat on the surface. This is if it's angled upwards, and then this one is something that's actually able to move and track the sunlight. Um, then you could, for example, get better in a lot of regions than you would even in the Southwest, where you're actually getting the most sunlight. And so that is one of the nice strategies that helps to sort of maximize the solar potential. Okay, we are a little over halfway. So let's take a quick 5-minute break, and come back at 1:14, and we'll continue onwards. In the meantime, I'm happy to take any questions that you guys have. Yeah, so there's a question, any difference in solar energy consumption in the West and the East? Yeah, definitely. There's a whole lot more solar installed on the West Coast than on the East Coast, so we use a lot more solar power. Actually, I did have that old chart. Let me pull that up. So if I open, I think I think it was the previous lecture, can show a map. Maybe it was that one. Yeah, here. Yeah. Oops. You can see uh, pink is solar. So there's a whole lot of it here on the West Coast because the resource is a lot better. And actually, this doesn't even include distributed solar, so solar on people's rooftops. And that adds quite a bit as well. So, I mean, you'll notice that there are solar installations on the East Coast, but if you compare the power produced from that solar versus the power produced on the West Coast, it's like order of magnitude different. So there is quite a big difference in terms of the production. Um, yeah. There's another question on the homework. What's a visual aid for the questions? Yeah, it's pretty simple. It's just if you think about the LCA boxes, so you just draw some boxes and arrows to make a diagram for like a fairly basic uh, description of what's going on. I think in mine I had made just like a like a production box and a use phase box, something like that. Nothing too complicated. Um, can I provide an example? So look to the LCA uh, LCA lectures. It really should not be really that complicated. It's like two boxes and a couple arrows. On the homework, should money values be rounded up to the whole dollar amount or including cents? I would go by the significant figures. And I'll be fairly sort of flexible here, but generally, I think most of the stuff is going to be like two sig figs. Okay, that seemed like a pretty fast 5 minutes. Let's continue on. Oh, what happened to this thing? Is this oh, my figure got a little messed up. So wind power is driven by temperature differences as well as the Earth's rotations. Um, I think this was a figure that's supposed to move. I don't know why it's sort of darkened out like this, but don't worry about it. We can get we'll see a couple other more useful figures about what the wind resources look like on the surface of the Earth. So here's our sort of back of the envelope for wind. So like a particularly good wind resource might be something like 500 watts per meter squared. So let's see, when I'm talking about what does that look like, let me actually just draw it out. It'll be easier to visualize. So if you have, well, use a color so it'll be easier to see. So if I have a wind turbine that looks like this, the wind resource that goes through the rotor, which is this area here, that's what I'm referring to with the wind resource. So per surface area of the rotor, the coverage that the blades span, that's the amount of energy that would be sort of going through. And so the speed of wind going through the rotor would be on the order of like 17 miles per hour, 7.5 meters per second. Once we get to the actual technical resource and when we start talking about the technologies and how they work, we'll give some equations that let you calculate this. If we are saying converting at 25% efficiency, which I actually think is a little bit low, you may be getting about 125 watts per meter squared. So the annual energy production for this one wind turbine would be about 1,000 kilowatt hours per meter squared per year. So over the same like comparable surface area, your wind is getting like 5 times more power than the sunlight per meter squared, but that's kind of a weird metric. I would not like have that as a number to keep in your mind. That's kind of comparing apples to oranges. In terms of technology application, so to power a conventional house, you would need a 5.5 meter rotor diameter. For a fuel cell car, 1.4 meter diameter, 4 meters squared for your battery car, which would be even smaller in terms of the diameter. The typical wind farm spacing is about 5 rotor diameters by 10 diameters. So what that means is like, let's see, if I'm looking straight at the wind turbine and it looks like this, and the diameter, if the diameter of the wind turbine is say, okay, what's a realistic one? Let's say this is like 50 meters. Sorry, that's kind of hard to read, huh? What if I do it in red? So if it's 50 meters, that just means that spacing wise, it's 5 times 50 for the next wind turbine. And then going backwards, it would be 10 times 50. So the spacing of the wind turbines is generally is roughly based on the diameter of the rotor. So 5 rotor things apart, side by side, and 10 meters back. Yeah, and the reason why you can do this, right? So if you think about it, actually would have like a actual model to demonstrate if we were in a class, but think about this mentally. If you were blowing at a fan, right, and the fan is spinning, and you put your hand behind the fan, it's not as though there's no sort of wind in the back, right? It's not capturing 100% of that wind, which is why you're getting not 100% wind efficiency. And so behind that, you could put another fan and capture some of that energy. And so there is some strategy in terms of like how you space out your wind farm to like maximally take advantage of the wind passing through an area. Okay, so this is on land, worldwide wind resource availability. you can see where the windiest parts are. So blue is not so windy, and then yellow and red are super windy. And so you can see in the Midwest of the United States, you actually have a whole bunch of available resources for wind power, and indeed, that's a lot of where the wind is located. Um, you have pretty good resources in portions of Canada, in the UK, and sort of Western Europe. There's a good amount. Um, in fairly remote areas, Siberia and in Russia, um, uh, in sort of the high plains in China, you have good wind resources. So a lot of these, a lot of the places where there are lots of people in terms of like population, so close to like Chicago, for example, in England on the west coast of Europe, they're trying to take advantage of this a lot, and there's been a lot of wind resources installed. In other cases, when you're more sort of remote, like northern Canada or Siberia, it's available, but it wouldn't really make sense to install a lot of it and then transmit the power, because the transmission lines can be super, super expensive, and you lose a lot of efficiency as you go long distances. So that's one thing to keep in mind. So we can zoom in on the U.S. here, and well, it's kind of repeating what you saw from before. Maybe you get a little bit more detail in terms of where the best wind resources are. But I think one thing to really pay attention to in this chart is right off the coast here. And so you could actually install wind turbines in what we call offshore wind, which are like out in the middle of the ocean, and you get suddenly really large amounts of wind resources. And so we'll talk a little bit about the differentiation between onshore and offshore wind, and what that sort of looks like practically in current day when we talk about the technical resources. One of the, as we get more into sort of nuance and detail about these things, kind of similar to, with solar, there's this whole thing about the angle and incidence. Well, actually with wind, there's a similar analogy for the height. And so if you actually build taller wind turbines, you could take advantage of greater wind speeds, which means you can extract more energy. And so this gives a rough overview of the wind resources at different elevations or different heights. And so this is specifically looking at sort of Bay Area, Central California, and you can see the relative wind resources at 50 meters, so 150 feet high versus 300 feet high, right? They can be pretty different. Or you can see progressively at these higher altitudes that you're able to get more energy. If any of you have ever been to Sweden, there's like a really big wind farm out there with I think it's got to be like thousands of wind turbines. It's a pretty remarkable sight. You may catch a glimpse of it if you go on the 680 to the Bay Area, or if you go across the bridge to Pittsburgh, Antioch area, you can definitely get a good view of this. And it's a fairly sort of remarkable sight. It's basically wind turbines as far as the eye can see, and they're exactly trying to capture some of this pocket of good wind resources right in this area. Yeah, I've actually visited in person before, and there, I'll just sort of anecdotally tell an interesting story when we talk about some of the environmental externalities and other sorts of externalities. One of the big drawbacks, which we'll talk a little bit in more detail next lecture, is this issue called NIMBYism, where it's like not in my backyard. People don't like having wind turbines there, located on land close to where they live, or on the ocean close to where they live, because they think it's like an eyesore. But there actually are positive benefits. The wind farm in Sweden is co-located on top of farmland that's grazing land for sheep. And when we visited, it was on a hot summer day, and all the sheep would line up in the shadow of the wind turbines to cool down. And so you get some positive externalities by providing shade to farm animals, which is pretty cool. And they sort of graze the grass in the shade of the wind turbine over the course of the day as it like moves. Okay. So in terms of the total gross wind power potential, the total estimated sort of worldwide, if we could basically capture everything in wind power, is 300,000 to 600,000 terawatt hours, which is like more energy than that is consumed by everyone sort of combined. So current use is about 19,000 terawatt hours per year. And we are projected to use 40,000 to 50,000 terawatt hours per year by 2050. And of course, that's like just one scenario, assumption, or forecast. It could be pretty different depending on how aggressive we decide to get. Alrighty. So that wraps up wind. Let's talk about hydropower. So theoretical resource, it's the energy carried by water runoff on land. And really what that means is potential energy, right? So runoff is always going from high elevation to low elevation. So think about water flowing from like mountains and rivers down to eventually your oceans. And so essentially what we're trying to do is to capture some of that energy. Otherwise, it's kind of just wasted energy, right? It's free, it's out there, it's flowing down anyways, and so you just want to be able to capture that. The global hydropower potential, there's a range, again, depends on assumptions and sort of who's doing the modeling and how it's being estimated. It's around 16,000 to 40,000 terawatt hours. So this accounts for geographic elevation, the magnitude of precipitation, and topography. A lot of the theoretical potential can't actually be captured because of basically inaccessibility and issues with siting. So it may be too difficult to build the dam, or you're not allowed to build the dam, that sort of thing. Another map, global hydropower potential. So the more red it is, the better the resources are available. You can see in the US, there's some yellow and red in the Pacific Northwest. And in fact, a lot of the Pacific Northwest, a lot of their power is produced from hydropower. So they're taking advantage of that. In South America, there's quite a bit of potential. And so a lot of the countries there, a large amount of their power production, the vast majority, can be coming from hydropower. And some resources in Asia, there are a fair bit of hydropower potential being taken advantage of and sort of increasing over time. It's one of the, I would say, easiest, reliable resources that unlike wind and solar, there is variability in hydro, but there's also a lot of flexibility in that you send water through the turbine, and you can kind of control that. In sort of aggregate, there's like how much water is left in the reservoir, and that affects how much you can do that. But you're not getting like hourly variation where suddenly the wind dies down or the sun sets, right? So hydropower is definitely a resource that is heavily taken advantage of in many areas, and from a cost standpoint, it's fairly competitive. It's it can take time to build, but the capacities associated with hydropower is usually quite a bit larger than for like a wind farm or a solar plant. You can generally get comparable amounts to like large coal plants from hydropower. Another sort of reason why people take it, or countries have taken advantage of accessing this particular resource. It is, one of the issues is that it is sort of unevenly distributed. There's still a lot of unrealized potential in like Latin America, Asia, and Africa. And so we saw some of that potential. And even though that some places are taking advantage of it, some still have that resource not sort of fully tapped. And so over time, there are a lot of projections that have looked at hydropower development, and in places like North America, Middle East, it's fairly flat, but you can see pretty large growth in Asia and in Latin America. Yeah, so the International Energy Agency, the IEA, has done some modeling studies where they think that hydropower could grow by a factor of almost by 2 in a lot of developing countries. As I mentioned, for hydropower, unlike solar and wind, you don't have intermittency issues, but there are definitely variability both over the course of a year. So this is a picture of well, not just rainfall and snowfall. So precipitation. So this is an example in San Francisco, but actually probably the more relevant one is thinking about precipitation at high elevations so that the water collects and then moves down. So a lot of that is similar to this in terms of precipitation, but it's actually snowfall. So when we think about reservoir levels, it's correlated to this, but it's not it's not at the same time. You'll have a lot of snowfall in December, January, February, and March. And then that snow will eventually melt during the summer, which is then when your reservoir levels increase. And so you may get rainfall that looks something like this, and then your reservoir levels may rise sort of over the summer and then decrease, something almost inverse of this. In addition to variation within a year, you also get a lot of variation across different years. And so this can play a really big role in the amount of hydropower that's generated within a particular year. So if you guys recall, like a couple years back, we were in like a mega drought, and I guess we're kind of continuing that this year. There's been pretty low rainfall this year, so we're going to be in another drought this year. And what that means is that in years with less rainfall, your reservoir levels are lower, and the total amount of power coming from your hydro facilities are going to be lower. And this has sort of rippling effects throughout our electricity system, which we'll cover in other lectures. But hopefully this gives you a sense that it's not a uniform thing where we just produce X amount of power from hydro from year to year. It can be pretty high in some years and pretty low in other years. Okay. Moving on. So thinking about biomass. So this is our sort of back the envelope calculations for biomass. You can have really good crop growth, 20 dry tons per um, hectare, and the energy value might be something on the order of 18 gigajoules per dry ton. Um, and so if we do that calculation, we multiply the dry tons by the energy value, you're getting about 360 gigajoules per hectare of land per year. It's about 10 kilowatt hours. So if I do the conversion to electricity and I do the um, uh, or electricity units, that this is actually pre-efficiency conversion. So just gigajoules to kilowatt hours, and then you change hectares to meters squared. This gives you a sense of the energy that you can get from the plant on a meter squared plot of land. I think one of the most directly comparable ones is for solar power. If you remember in the back of the envelope, I think we were closer to about 100 kilowatt hours. So you're talking about a tenfold difference order of magnitude. Does that make sense, right? I think so, because you can sort of logic this out in your head. Right? If I have the same amount of sunlight that's growing plants, the actual growth of the plants is it's not perfectly efficient to convert all of that plant energy into biomass, right? So you lose a lot of the energy there compared to losing the energy in the solar panel. So if you convert it to electricity at 30% efficiency, it's like 3 kilowatt hours per meter squared per year. If you convert it to fuel, which is you would do for transportation, for example, then you could get something like 216 gigajoules per year. To fuel, fuel
Alan, I don't know if you can hear me.
Sorry for everything. I'm going my iPad.
Is it back?